go up there. So I don't have to look over there the whole time. Until then, turn off flex forever. Bring this over here. Oh. Peek behind the curtain. Alright. There we go. That guy's going to take a minute. I'm going to go stand outside the main. Hello. Because I didn't announce it or not, I should have done that.
Is it in the Slack channel?
Someone sent a message. I also forgot to add channel. I made a lot of mistakes with this one. Busy with that mistake.
Yeah. Did you intentionally put them right next to each other, or is that just how it lined up?
How it worked out. I wish it was intentional.
How many presentations do you have?
3. One by Ian Furr, the other one, or one by Nicholas O'Brien, and one by Peter Willis. You'll see him in the slides. That I now have to refresh because I got the order wrong. Okay. Golden? Yeah, well, we are live on YouTube. Stream health is orange. We have one viewer. I think it's me. Not positive. I'm gonna quick grab a link to this. We're on YouTube, the RIT NextHop account. Boom. We have 96 people in this Slack. All right, we're gonna get started. Thanks for coming over, everybody. We're NextHop, in case you didn't know. Be surprised if you didn't. My presenter view isn't showing up anymore. That's gonna be awkward. Starting off on a great note. If you haven't already signed in, please do so now. Because having a good accounting of who's coming to the meetings helps us continue to be a club. So elections are going to be coming up soon. If you're interested in running for the NextHop e-board, fill out that form, nexthop.network/nominate. The responsibilities are pretty open-ended. We've kind of switched over the years on some of the things that we do. For instance, I manage most of the communications with like the club center and arranging all the events and everything. Even if you don't have any experience with like running a club, or if you're kind of young to the school, I would still recommend that you nominate yourself or someone that you know, because it was a great experience for me so far. And I'm sure it will continue to be for the next couple of weeks. It's one of those things where it's like a small enough club that like you can afford to make a couple of mistakes with managing, and it's not going to cause like huge amounts of problems. So those are the current people who are on eBoard, and their Slack handles. If you want to shoot us any messages about what we do, we'd be happy to answer them. Okay, so NSIC was this last weekend. Here are the teams that won again. First place was Land Before Time. Second was Threadrippers, and third was Domain Name Saviors. If you competed or volunteered, please provide us some feedback. It'll help us run the competition a little better next year. Just let us know, honestly, how we did, where we can improve. We would really appreciate that. Our next building night in 2 weeks is going to be just a recap. Some of the stuff that we went over at NSIC. Be available to ask any questions that you had about the scenarios or the challenges, or really anything that you want to ask us about. That's, yeah. So we will be there March 20th, 6 p.m., SysLab, just like we always are, except for when we're here. So without further ado, these are the presentations that we're going to be having done today. First, Ian Furr is going to present home automation with Home Assistant. Then Peter's going to talk about his cool grad project. He didn't give me a title of his presentation, so I came up with that one. And then our final presentation will be by Nicholas O'Brien, Elliptic Curves, a spicy introduction. So Ian Furr, if you want to get on up here. Yeah. I mean, in theory, because you sent me your slides, I could display them, but I don't want to.
I updated them, so it's probably...
Oh, even better. Yeah, you took out all those cuss words and everything, right?
Oh, yeah.
There. If you want to just throw your stuff in there, it'll automatically get streamed to the inner tubes and up on the screen.
The inner tube?
Yeah, the inner tubes. You know, that thing you use for Google?
Is that the technical term?
Yeah. It's also what you use to connect to virtual PNs to do your naming.
All right. Awesome. Oh boy. All right, cool. So,
Keep doing what you're doing.
all right. So this is home automation with Home Assistant. So who am I? I'm a second-year CSEC student here at RIT. I'm a home automation enthusiast, and just a fair warning: half of the time, most of the stuff in the house is broken. So what is Home Assistant? Home Assistant is a Python-based home automation platform. It's open source, and in my opinion, it's probably one of the best things ever. There's a small demo up on Home Assistant.io/demo, and that's the official one that the creators of Home Assistant put out, just as an introduction to the platform. So there's a whole bunch of ways that you can get started with Home Assistant. They've got a whole bunch of different installers, the all-in-one, Haspian, Windows, Mac, Docker, Has.io. It's probably one of the easiest projects I ever started. I just had to flash an SD card, plug it into my Pi, turn it on, and all of a sudden it was up and running. So the way Home Assistant works is once you flash it and plug it in, it's got an auto configuration recognition phase where it will look on your network to see what kind of devices that it knows about. So in my case, it was Philips Hue bulbs, a Wemo outlet, a bunch of other just small things like the Google Homes and our Chromecast. And all of this stuff is automatically picked up by Home Assistant and configured so it's ready to work almost right out of the box. So that's actually a picture of my mess of home automation setup. I've got 2 Raspberry Pis running, one in the little black case and then one in the clear one. The clear one is running Dasher, which lets me use Amazon Dash buttons to interface with REST APIs, and it interfaces with Home Assistant really nicely. So we've got a bunch of those scattered around the house for reminders like laundry and the dryer and the dishwasher and stuff like that. So I love Home Assistant because it integrates with almost everything. It's super easy to set up, it works great, and there's a huge community out there of people that really care about the platform and support it. It's been around since 2013, I think, and it's been getting constantly updated and new things are constantly being added. So there are a bunch of different parts of Home Assistant, and this is just kind of a breakdown of one of the menus. So the overview is just a view of everything that you have installed on the platform, and that's where all of the new sensors, all of the new configuration information, all that stuff shows up. Map actually brings up a map, and if you've got presence detection and GPS tracking set up for devices you have attached to it, then it'll put those things on the map. I have OwnTrack set up on my Android phone, and it will put my phone somewhere on the map to actually see where it is. Logbook just shows all of the state changes that Home Assistant goes through. So if a device updates or a sensor trips or something like that, it'll appear there. The history is a chronological timeline of all of the states of the devices. So if somebody comes home, it'll update in there and in the logbook. And then the configuration has a bunch of options for configuring everything without actually going into the YAML config files and format everything that way. So it makes it a whole lot easier to get into if you're not familiar or if you hate YAML. And then down the bottom, there's the services, states, events, templates, MQTT, and info. So these are all just a bunch of subcategories in the configuration menu. So the really powerful thing about Home Assistant is that it offers automations and scripts. So whenever it detects a change or a trigger of some sort, then it'll fire off an event, and you can configure that event to do whatever you want. You can hook it into Node-RED, which is an IBM framework, I'm pretty sure, that enables flow-based management on a lot of things. So the triggers, there are events, which are things firing off after certain conditions are met, like I mentioned, coming home, or a light turning on or off. Home Assistant just has options of Home Assistant coming up or Home Assistant going down, so you can set up a bunch of things to run once your system comes back online if it dies for some reason. So over here, I have just a simple little animation to turn on my lights, and I made it orange just because whenever my phone changes from not home to home. And the presence detection is just based off of if the router, I've got an Asus one, so it just hooks in and it with SSH, and it'll detect devices on the network when they connect. So home automation has over, I think, almost 1,000 integrations now, and it integrates with things like Alexa, Arduinos, Google Homes, like I mentioned, OwnTracks, Pushbullet, Wink. We have an integration with Discord, so I can at my roommates through the Home Assistant channel, and it'll notify us when stuff is happening. There are automations that can set up specifically through here. You can set up views, so you can monitor cameras. So if you've got security cameras or something like that, you can just throw the views up in Home Assistant. Like I mentioned with the lighting, I've got my Philips Hue hooked up, so I can turn on and off my lights through the web interface, that kind of thing. Yeah.
What's the how do the integrations work with like Echo and Google Assistant?
So those ones are a pain in the ass to do.
You can swear.
Those ones are a real pain because you've got to set up an external service or something like that. That way you can hook into the APIs that Alexa and Google Home have. I haven't been able to get the Google Home working, but that might just be because my network is real screwy.
Interesting.
Yeah, but they just started offering a service called Home Assistant Cloud, which they do for $5 a month, and they offer a hosted box where you can just direct all of the traffic at that, and it sets up most of the stuff for you.
Awesome.
Yeah. So this is just an example view of Home Assistant. This is the one I have at my actual house back in Connecticut, because the one I have here is down at the moment. Oops. So over here I've got weather, and it just pulls weather from the Dark Sky API. You just throw in a key and tell it what parameters you want it to check, and it'll pull everything every 30 seconds. Up top is a configurator for Wink. So when you add new devices that Home Assistant can't automatically talk to, it pops up with this configurator, and it lets you just click configure, and it walks you through adding new things. So with Wink, you need to add an account and an API key and that kind of thing. So with the Google Homes, you can use them as speakers and cast to them, but if you want to actually send commands back through the Google Home to Home Assistant, then you need to go through the configurator and add the API keys and set up the Google apps and all that mess. So whose home is just presence detection. There are a bunch of names and pictures under there. I just didn't want to show them to the internet. So it just tells you if it's home or away, and if you set up GPS tracking, then it'll actually give you locations if you set it up that way. The sensor nodes are just two ESP26 somethings that have a bunch of things coming off the GPIO pins. So I've got an LED, humidity sensor, light sensor, and a motion sensor, and a thermometer. And all of that stuff just updates, and it hooks into a table, and it just logs everything. And we use that because some of the rooms in our house are wicked cold in the winter. So we use that to hook into the thermostats and fire it off whenever stuff's getting too cold.
Wow, that's awesome.
Yeah.
Do you have like a Nest, or is it just
It's really
you look at it?
it's really jankily wired. So not through a Nest, just lots of cables sticking out of the wall.
Nice.
Would not recommend, just get a Nest. Or an Ecobee. Those are even better with Home Assistant. So that temperature graph is actually the temperatures we have through those sensors. And we also have a Z-Wave stick hookup to this, which is another protocol similar to most of them, but it's wireless, so you plug in a stick and you hook it up to a lot of the smart home devices like outlets and switches and stuff like that, and that creates a mesh network, and you can talk to all of the devices once they've been activated. So that's how we have a bunch of the lights and stuff like that. And we used to use the Wink, but we've been transitioning away from it just because that requires a web server running in the cloud, and this is all locally, so we can, as long as we have power, we can turn off all of those lights. So, any questions? What's up?
So if you have two homes, say like one here and then one in Connecticut, are you able to like link them up together in order to like see them both like side by side and compare?
So with the cloud, you can actually send stuff out, and there are a bunch of other ways you can do it. You can send it to MQTT servers, and you can have that store state, and you could just measure state as a sensor through Home Assistant if you wanted to. Pretty much, as long as you're able to get that data out anywhere, you can read it into Home Assistant in some way or another. Anything else?
How does this work in a more complicated, like I know you said your network is more complex.
Mm-hmm.
How does it work with discovering places like across subnets?
I have no idea because I haven't had to test it. You can specify routes to some of the stuff, but it might not work perfectly 100% of the time. I know there's a significant delay if I'm going off network, if I'm talking to the Connecticut home from here, but it'll still recognize some of the stuff occasionally.
So real quick, I had a question for someone watching the stream. What is the name of the product again?
Home Assistant.
Home Assistant.
Yeah, in the next slide, I've got a bunch of resource links. So The Home Assistant website is home-assistant.io, and that's where you can find the downloads and the forums. The subreddit r/Home Assistant has a ton of people that are super helpful, and they're really awesome. I had a couple questions that I went onto there, and they've got a bunch of examples and stuff that I pulled a couple things for inspiration from. And then Bra Automation on YouTube is an awesome channel to get started with, just because he walks through a lot of the things that might trip people up if they're not familiar with using Home Assistant. And then they have also got a Discord, which people can jump into and use from there. Awesome. So, thank you guys.
Thank you. Yeah, next up is Peter. Thanks, Ian.
Hello. All right. Sorry. For those who don't know me, my name is Peter Willis. I was a networking systems administration student in the undergrad degree. I graduated in May of 2017, and this past fall semester, I started the graduate networking systems administration degree. When I began, I also became a research assistant, and this is how I joined on to this project, which is the mesh tree protocol. It's headed up by Professor Nirmala Shenoy in the IST department. So I'm going to go over kind of what I know about the protocol. It's gone through many iterations and versions over the years by different people. There's a lot of different features to it that are kind of half-baked or not fully ready yet. So I don't know everything, so I apologize if you guys have questions and I can't fully answer them. But from my perspective and what I know about it, it's at layer 2, the data lake layer. And it's a novel way of preventing loops in a network, because obviously frames would forward forever. And it tries to improve upon, obviously, what we already have out there now. This is actually currently an official IEEE standards project, 1910.1. So it's already kind of gained traction in industry. We hope that big companies like Cisco can kind of pick up on this as well, so we can kind of keep the process rolling. The main part about this that's novel is this idea of mesh trees. This is a completely novel idea. So obviously we probably all know about what a spanning tree is. What a mesh tree is a collection of spanning trees that come from a single root. They do loop, or they do have loops in them, but only certain ones are used at a given time. So you're using all possible links, but not at the same time. So you're still not having those looping problems. To join a tree, you're given a VID, a virtual identifier, and that kind of signals that you are part of a tree. You can be in up to 6 different trees, so you have 5 redundant paths by default, but there are more possible ones, so if you were to lose some, you can gain more. Currently, the protocol has 3 different control messages. We have a join, a hello, and an advertisement, and I'll get into that in a little bit. So just to kind of go over what is already out there, obviously in customer networks we have RSTP, that's kind of the standard 802.1W that's built off obviously the original STP, which is fine enough. Convergence time is pretty good, but you still have that problem where you only have one active tree, so you have blocked ports, and we're trying to prevent the idea of blocking ports. We want to preserve the mesh nature of switch networks. On the provider side, I don't know if you guys have ever heard of this stuff. The 2 big ones are Trill and SPB. SPB is actually a creation from Radia Perlman, who was the developer of STP and RSTP. It really hasn't taken off, so this is kind of where other protocols like MTP come in, where we can kind of try and fill in the gap. They're much more complex as well, that use like the ISIS link state routing. They use Dijkstra trees. It's not kind of simple that you see in RSTP, and that's kind of another main goal of MTP, is to be very simple but still provide that loop-free topology. And kind of going away from loop avoidance, obviously at layer 2 we have different protocols to do different things. RSCP for loop avoidance, VTP for VLAN propagation, DTP for trunking, and that's fine. One of the eventual goals of MTP is to be the layer 2 protocol that can really do everything. So just to go over a few of the components, some of our acronyms and such. An MTS is a switch that is part of an MTP domain or an MTP tree. The VIDs, what I described earlier, are these virtual identifiers that are very similar in nature to what an IP address looks like. So it's a dotted decimal system. Unlike IPv though, it is variable length. So the larger the topology, the longer your VIDs are going to be for each tree. These VIDs though help define where you are in the tree. I'll explain a little bit more about that later, but you're essentially at each node, you're appending a new ID onto each VID. And then frame forwarding is still really a work in progress. It's very complicated at the moment, but from what I do know that we have a primary tree, and that is the tree that is used for broadcast traffic. And then obviously, just like in RSCP, we have ports that are part of the MTP domain, our mesh tree ports, and then host ports that are just end node ports. So obviously, it's not very complicated. Type 1, it's just a join, it's just 8 bits. This just signals to a MTS that you would like to join the one of the trees. And from a join, you get an advertisement back, which will come up after this next type. And a hello, obviously, again, just an 8-bit thing. 8 bits in length, excuse me. This is just like a heartbeat that makes sure that your adjacent neighbors are still going and that everything's okay. 3 missed hellos constitutes a bad segment. Link failure is also in progress as well. It's something I'm developing right now. But for now, we also have this ability to prune based on hello times. And then finally, the advertisement. This one's a little longer. This is the actual message type that exchanges the VID information. The first 3 fields are this static header that obviously is your messages type. There are 2 types of operations. You can add a VID or you can delete a VID. And then the number that's contained in the actual advertisement. And then for each VID, you have the path cost, which is just the number of hops from the root, the length of the VID, and then the VID itself. And so as I kind of mentioned earlier, the VID, when you're actually placing it in the header, you take what your current VID is, so let's say it's 1.1, and you append the egress port number that you're going to be sending it on, so let's say that's 2, so your new VID for that downstream MTS would be 1.1.2. And then these are used to actually exchange information. You don't, the receiving node necessarily doesn't have to agree to it. That's why currently, if you do receive an advertisement and you accept that VID, you send the same one back to your upstream node so that he knows that he accepted it. And he can place it in what we call a child PVID table. So just to kind of go over a small topology, 5 nodes, nothing crazy. The numbers are the port numbers, just 5 nodes. Top left obviously is the root. So we can have one tree here, and then these numbers in the black are the VIDs. Usually they have a dot in between, but just to make it easier, it goes through. And obviously a second tree would be something like this that starts on the other MTS. And then with mesh trees though, you have both available to you. Obviously they loop, but you're only using one at a time, or a subsection of one at a time. So something that another student that I'm currently working with is working on, kind of what I mentioned earlier about how we want to bring more functionality to MTP than loop avoidance. VLANs is another thing we're trying to input. The way this would work is instead of a VID that starts at like 1, let's say, or whatever inputted number, it would start with the VLAN ID, and this would be able to propagate throughout the topology within the VLAN. It would help build out a per MTP tree. So I do have a short video just to kind of, 1, to show you kind of it in action, and 2, to kind of show what my work is like on Genie, which is a test bed for future internet research. That's where we do our work. And kind of how I go about actually testing things in kind of a more formal research environment. The test will consist of a 17-node topology written over the years by a number of people, including myself. And then we also have automation scripts that kind of do all this stuff, because obviously I don't want to go to every node and start it. And that wouldn't work for timing and such. So just to go a little bit about Genie as well, obviously these act as switches, even though they're just simple boxes. What a switch network would act like. I kind of talked about the automation already. And then we have what they're called slices. That's our topologies. We have topologies ranging from 3 nodes to 30 nodes, so one bigger than the 17. And currently, which is really what I've been working on these past 8 semesters, to get that, to get our MSTC down, and that means MTP single tree creation, the time it takes for one tree to be created, which means frame forwarding can occur. When I started, it was about 3 to 4 seconds, and we've gotten it down now to about 236 milliseconds, and it's legit. I hope it continues to drop as well. That number and that idea is really where we hope mesh tree protocol is going to really take off, because just the way it's implemented, it should be faster theoretically than how RSTP propagates and such. And just so you guys get an idea of where we're going with this, I have another student I'm working with who's working with OVS switches. I don't know if you guys have ever used those, but he's working with those to create a comparison to RSTP. So he's using the same size topologies and doing the same single tree creation kind of idea. Obviously, there's only one tree in RSTP, but then we compare the results. And then, as I mentioned earlier, link failure detection is something I'm currently working on, and it's going well, and hopefully we get that out by the end of the semester as well. All right, so let me switch over to the video. And I'll probably skip through a little bit of this. So just to kind of show you, this is Genie. You could have a number of these topologies, as I showed, from 3 to 30. Each one is just a box I can SSH into. And you build them like it's like a video game. You're putting them together and linking them together. It's cool. So we'll skip probably through a little of this. All my work is also done on Linux machines as well. So this kind of just shows, this is a script I wrote or helped write to start the protocol. You can skip a lot of this stuff. It's just transferring the files over to all the nodes. Then I run it again to actually start the protocol. I input a time. Part of the testing is making sure every node comes up at the same time so we can get correct results for convergence timing. And what you see here is that's what it's doing now. It's inputting what the node is and what it needs to be doing. Obviously, one of them will be the root and the others will be waiting. Skip through that. All right. And so you can see here, like I mentioned, it's just, you just SSH to the box like you would any other. But obviously now that the code is in there, a little bit. I don't know if you guys have ever used GNU Screen as well. It's like it emulates a second terminal within the terminal. That's where I place the MTP code, so it's in its own little environment. And then I have this script within that gets transferred over that sleeps for a certain amount of time, which claims down to nanoseconds. Oh, there we go. Okay, so this, once that gets out of the way, this is a lot of the actual print output that we use to see what's going on. What's this? Oh, well, it's not going away. At the bottom, okay, there we go. So there's 3 main tables, or 4, excuse me. Our main VID table, our backup table, our child PVID table, P being primary, and then our local host broadcast table. There are no end nodes in this topology, so that's empty. The child table is if a advertisement were to go to a downstream node and it would accept and send it back. That's where you would get an addition there. And then the main and backup are the same. We limit it to 6 VIDs. When I started, there was no limit, and in a 30-node topology, there could be 15 plus trees, and the actual lengths of the VIDs were 30, 40 characters long, and they were getting insane, so we kind of pruned that a little bit. So you still have 5 backups. You can kind of see to the right of the VID, and that's kind of where I mentioned it's kind of IP-ish. The name of the Ethernet port it came on, the hops, which is the path cost, and the membership is just how it ranks, and then the MAC address of where it came from. You can kind of see above that too. I've done a lot of print statements on, you know, how to, where to place the VIDs and which one should be the primary tree and such. And then the rest is kind of just showing stopping the nodes and then collecting results. So in this way, I can test each topology very quickly and get results out faster, which can go into papers, and we can try and get published this way. So which creates a log file, which compiles. What you see here is the first number is a time in microseconds, and then the time below it is the absolute time, which is what I record. That is the time that a VID is added to the VID table. So obviously for a single tree creation, we are dealing with the first entry in each time. So you can see here the MSTC time, so 170,427 microseconds in this test for a 17 node in this case. It's pretty good. I don't think anything else super crazy happens. Okay, so this is another file I also take. This is every control message that is sent, and then the actual time it's sent. So you can see at the beginning, there's just a lot of joins being sent because the trees need to be built, and people need to signal for the trees, and then the trees are actually built once the advertisements are sent and received. Advertisements are flooded out of all other active ports when they're received, so all other neighbors can be updated. You can kind of see there some of the VIDs that are being sent around. It's kind of cool, just so I don't have to go into everyone and see what's going on. Some more there. I think that's about it. And obviously, once everything starts to stabilize, you have a bunch of hellos that are just going back and forth. I think that's about it. Yep, back to the Genie topology. And that's basically, at the moment, in TP. We're hoping it, you know, really takes on traction. We've submitted to a bunch of contests and publications and stuff, hoping we get, you know, more, we get the word out, I guess, and you know, hopefully one day you guys use this in your everyday, you know, life as network engineers. I hope. We'll see. But yeah, that's MTP. Yes.
So what's it been like trying to write things that work for a protocol, like programming stuff? Like, what's it been like working at such a low level?
It's weird. Before joining up as a research assistant, most of my work was in Python, and I was told I had to code in C. So, you know, the difference there was pretty jarring, to be honest.
Did you already know C?
No, I had to learn it.
You know C now?
Yeah, kind of. Does anyone really know C? I got the job at the beginning of June, and I started in August, so I kind of had a few months to learn a few things. I mean, I still procrastinated on learning it, but like,
you know, this is being straight, right?
But it worked out. I'm doing okay. There was a good base for me to work with, and it is fun. C is kind of fun in a weird sort of way. It is interesting though. It's kind of changed my perception on how protocols work, because obviously when you're a networking major, you just get taught, IP does this and TCP does this because, reasons and, whatever. But to actually see it like being built down at that level, it kind of gives you a new perspective on what's going on. It's a cool feeling. A lot of low-level sockets. Everything is raw sockets. We deal with everything. Yep. It's sad. And obviously, of course, every once in a while I'll do a Wireshark capture. I'll get a PCAP of this stuff. And Wireshark doesn't know what the protocol is. Yeah, and I've seen so many. If you give me an advertisement message, just the raw hex, I can tell you what it is. Like, it's bad. I've seen too much of it. But yeah, it is. I mean, we have functions to send, just functions to send on Ethernet and all that stuff. And it's placed right in Ethernet 2 header 2, if that wasn't clear. yeah, it's a good time. It's fun. Yeah.
So, what would you say are some of the drawbacks of this compared to RSTP?
Obviously, RSTP it kind of has that. Has all those years put in on actual networks. If we were to actually put this on Cisco switches, I don't know how it would work. I don't know how it was gonna, everything is pretty much built at this point for Linux systems. So that's kind of a problem right now. Otherwise, there's just the whole idea of variable length tree addressing is still kind of a work in progress. I don't know if any of you guys were at last year's Tech Talk where Eric Golan spoke. He spoke about MNLR, which is another project headed up by Professor Shenoy. It has a lot of the same concepts in it at layer 3. And it's kind of facing the same thing where variable length addressing is kind of a weird idea on how to build these trees. So there's that. And then, of course, at the moment, actually, as I kind of mentioned earlier, unicast frame forwarding is actually really complex. I had to sit in with a student that did his thesis on MTP unicast frame forwarding, and I have like 30 flow charts, and I don't know really how any of it works right now. I have to go over it again. So there's the actual frame forwarding part we really need to get down as well. But it is really getting there. A lot of the code is already written, and when it is used, it works pretty well. So it's just immature. It's still in its infancy, and I think it needs time to grow. And we need to find. There's still a lot of bugs too. And sometimes things happen, and I'm like, I don't even know why I did that. Yeah.
Do you think this is a protocol you could see get picked up and used in the real world?
God, I hope so. I really hope so. I mean, I've spent literally hours with this thing, and I really do believe in it. I think it can be a real thing. Who knows, really? I mean, it's the project. The IEEE project's been around for a few years, and right now it's kind of in this limbo state where we really need to get more publications out. That's the focus right now, is to get it into major conferences and publications. There is interest in it. We have received emails and queries and such for it. It's just a matter of actually finishing that, and then by the end of the semester, we should have something ready.
How many vendors have reached out?
We had a meeting with Cisco. I don't know what came of it. I'll have to ask Professor Shenoy. I think they like to see this kind of stuff just to kind of get ahead of the game about what's coming out. Yeah, I don't actually know how that went. I should ask.
Because with the Cisco switch, I think it would depend on what the version number in the frame is, and if they do like Fogon rejecting. So they're not going to expect your version number for the information in the frame.
That is true.
The switch will either just drop it or go, I don't know what that is.
Yeah.
Here you go.
Yeah, hopefully it maybe not Cisco, maybe Juniper or some competitor would like to see it and implement it. They're pretty adamant on RSTP right now, and to an extent, what I mentioned earlier, the trills and the SPB stuff, they are really still trying to push that. It's just not going anywhere. So when they finally get over that, maybe MTP can come in and steal the thunder a little bit. But yeah, I think I've taken up enough of your guys' time. Any other questions? No? All right. MTP.
Okay, thank you, Peter. So our final presenter for the evening will be Nicholas O'Brien. He was going to talk about elliptic curves, but in a dramatic twist, decided to switch to talk about something else at the last minute. So give it up for Nicholas.
Turn off Flux. It's awful. Also, put up your answers for that CSET 360 homework.
You can't see it, it's fine.
Yeah, you perfectly obscured that.
All right. So as was mentioned, I was originally going to do elliptic curve crypto. I mean, I guess if there's a mass cry out for a change, then I can go back to that. But I thought that it might be more interesting to do quantum computing. So
Let's do both presentations.
yeah, how much time do we have? Okay, so that's going to be the topic that we're going to go with. So who am I? I'm Nick, fourth year student. My majors are comp math and CSEC, so that's cool. I guess I'm technically a grad student, kind of. That's what I tell co-op people. And my main topic area that I look at is crypto and math. But it turns out that like not a lot of people in computing really care about quantum computing yet, at least to the depth that's needed, except for crypto people. And it's mostly coming from the sheer number of things that you need to know about math to really get into it. And I guess we have physicists, but really it's been left up to the crypto people to deal with. So I guess I had to deal with it. So where I'm starting, now I'm not going to make this, like I said, it can get complicated, so I'm not going to really go into the physics aspect at all of this. I might put out some physics buzzwords, but I'm going to explain those, and we're not going to get that in depth with it, because it gets crazy, really crazy. But I am going to do some math here. It's not that scary. It's going to be matrix operations, and I'm going to tell you how it works. So you really just need to know how to add, I guess. So I think we got this. And really, unfortunately, there's no crypto knowledge needed for this talk. That's a frowny face, but all right. So scary slide. So the math background behind this is, like I said, matrix multiplication. And a lot of us have probably possibly seen matrices before. I think it's kind of common. What?
So networking and systems administration students don't have to take linear algebra.
Whew, that's okay. It's fine. So actually, it might be more beneficial to skip this slide, and I'll just show you what happens. So as you can see here, we have like this matrix, that's what a matrix is, by the way. I think you've seen them, probably seen them. And then there's this column that's all ones, and everything else is zeros. When I apply this matrix, this particular matrix, it shifts everything over by one column. Okay? Pretty straightforward. If I do that again, it shifts it over again. Pretty cool, right? That wasn't that hard, wasn't that crazy. So it kind of, this is like all absolute, and this is precise, and this is what happens in each stage that this occurs, right? You apply this other matrix, and it shifts everything over by a column, and you get the new state, right? So it's like a state, and this other thing is just like changing the state, right? Here it's just shifting over column by column. But what if we wanted to get fancy, right? What if we wanted to assign probability to how it changes? And that's where this comes in. So see here, I'm starting with my ones all in the center, and then don't worry about coming up with these matrices at all. Don't worry, I did that for you. I apply this fancy matrix, and it actually gives this cool type probability distribution. So it says, with 30% chance the column shifts to the left, 30% chance it shifts to the right, 40% chance it stays in the middle. So that's kind of cool. And where it gets really interesting is when you apply that twice, right? Because it's really complicated to try to think about, well, I got to consider, what if it moved once originally? Now, what's the chance that it's going to go back to where it was? And then I have to add up, gets complicated. So what you can do is just multiply again by this change matrix, and it handles it for you. And we get this cool probability distribution that you see here. And apparently, with those probabilities, that's what it looks like in the end. But that's basically all you need to know about matrices. So it's just that they can be used to change states, and that's it. And they can represent states. So not too bad. Except for one thing. And that's because physicists like to make things hard. So what they have done is, instead of just regular numbers that you're used to, right? For probabilities, you're dealing between 0 and 1, right? Fractions, that kind of thing, right? 30% chance, 0.3. They take it up a notch, and they use complex numbers, which we're not really going to get into, except for the fact that what that allows them to do is deal with interference, right? So if for some reason two different changes would cause some type of interference, the only way that they can account for that is to use complex numbers. Again, we're not going to get into the math behind that, but that's the only way that they can do it. And they also have this function that they use to transition back to your normal probability, so people actually can make sense of all of it, because not everyone's a physicist. So that's all there is now. We're almost done with the hard math. It's fine. And this is the one complex example I've got. So maybe, probably not, but possibly, you might have possibly heard of the double slit experiment. If not, it's really easy to explain. You shine a flashlight at this wall with 2 slits in it, hence the double slit experiment, and it shows this really cool pattern on the back wall. And for a long time, people were like, why? Why is this happening? You would think that it would just be 2 slits. That's not what happens. It's really remarkable what happens. That is not what happens at all. And the reason why is because as light is transversing through the air, it acts as a wave, and it causes interference with itself. And that causes these bands of light on the other side. And we can use this math that we were just dealing with to represent that, and it's cool. And that's really this complex example. That's all you really have to worry about here. Cool. The only thing is, like, remember that function that I just hinted at a few seconds ago, where like they take their crazy probability and they make it into real world probability, what you would normally think of. Because of that, when you look at these, they almost make no sense at all. You're like, where is this 1 over square root 2? What does that even mean? What is that? That looks insane. And it comes down to that function. So if you run these 2 numbers through the function, they come out to 1/2. And if we look over on the side here, there's a 1/2 chance that it goes into the top slit and a 1/2 chance that it goes into the bottom slit. And then from there, each slit can basically only reach the 3 closest targets right here. And that's actually, guess what? These numbers right here are 1/3. So almost makes sense. It's cool. And this is what the change matrix looks like. Again, you don't really have to worry about that, but just a cool little tidbit. So when you talk about quantum computing, that was just a math precursor. That's it. When you talk about quantum computing, you invariably are going to talk about something called a qubit. Just like when you talk about computing, you're probably going to talk about a bit. And they kind of serve the same function here, right? It's the way that you save information, logically. The only difference is, right, with a classical bit, it's either 0 or 1. But with a qubit, you have probability associated with it, right? So there's a probability that it's 0, and there's a probability that it's a 1. And you don't really know what it is until you observe it, which is actually an action. You have to you observe the state, and the state finalizes, and that's what you get as your result. This is getting into how that works. That's quantum physics, but this is on quantum computing. So so they use these complex numbers that I was just talking about, these crazy looking things, to represent what's the probability that it's 0 and what's the probability that it's 1. The only stipulation is that the probability must add up to 1, right? You can't have 65% that it's a 0 and 65% that it's 1. That doesn't really make any sense. You're not really working with any useful system. Yes. So that's really how it is. Again, this important tidbit at the bottom, technically the qubit's always in that state before you observe it. You just don't know what it is. And this was a point of contention up until like recently in the physics world, where there was these 2 sides, and they're like, no, it's not in that state until you look at it. And then the other side going like, no, it's always in that state. You know, classic political problems. And, you know, they've decided together, in unison, mostly, that it's always been in that state. When you don't know what state it's in, again, it's in an actual state. We call that superposition. This is a physics buzzword. And that's really all there is about that. Now, you might be wondering, so you have this fancy qubit nonsense. What do you really get out of it, right? So like you have, take a byte, right, 8 bits. You can only have 2 to the 8 possible values attributed to that. Now, if you think of a qubit, right, consisting of 8 qubits, you don't just have 8 possible values. Every single qubit has a probability that it could be, right? So like if you just look at one qubit, it doesn't have just one value that it could, or 2 values that it could be. It could be any type of probability there, right? It could be 1%, 99%, 2%, 98%, anything, right? And because of that, you have a lot more information in one qubit. In fact, the saying goes that for 8 qubits, to represent that in regular bits, 1 second.
Notification?
No, not notification. I'm trying to make sure I got this right. Yeah. So.
I hope you did. You get the presentation elsewhere.
Yeah, right? Yeah. So in order to have 8 qubits, you need to represent 2 to the 8 complex numbers, right? So those are those values, the probability values, because you need to represent each value for each qubit for the entire thing. And that's just a lot more way to wiggle in data, right? Like that just gives you so much more freedom with a lot less bits. That's pretty cool. The other thing is, when you think of a normal computer, right, how you change bits values or even bytes values, you send them through logical gates, right? We're all accustomed to these ands, nots, XORs, ORs, you know, tons of different cool stuff. But with quantum computing, you're not restricted as much to just these whatever 5, and everything spans off of that, possible gates. Right? It's literally any matrix, change matrix that you can come up with that would do it. And because of that, there's a lot of quantum gates out there. People come out with quantum gates every single day, and they're like, hey, look at my quantum gate, guys. And they make a paper on it, and it's awesome. Until everyone's like, that's not useful. And they're like, well then. So it's kind of a tit for tat thing. But so that's cool and not cool at the same time. It makes programming hard, but yeah. So it's kind of cool. And the other thing to note here is that when operations occur, it applies to every single qubit at once. So it's not like it needs to happen 1 bit at a time, like in classical computing, on the low level. It happens all at once. So if you have 32 qubits, your matrix is literally just going to apply all at the same time to change those probabilities. That's all that's happening when you do a gate, a quantum gate, right? You're just changing probabilities as you go. Like we saw with the change matrix before, right? We're just shifting the column or whatever we're doing, right? We're swapping 2 percentages if it's just a regular qubit. That's actually one of the most popular quantum gates, is swapping probabilities between 0 and 1. So it's kind of like a knot, but it's its own thing. Cool. So all of this freedom has led to crazy new ideas in this realm. And one of the coolest is that, like, they literally needed to come up with a whole new section in theoretical computer science for classifying how hard algorithms are to compute. Because they're like, we can't really use this typical, is it polynomial time or is it whatever, however complex it takes to run an algorithm. We can't really do that anymore because quantum computers just work differently. And if we did that, everything would be so fast and it doesn't make any sense. So they literally came up with their own thing called bounded quantum polynomial, and there's all this other stuff that goes into that. Reliant problems, cool. So the other issue that comes up, and this is why crypto people are interested in it, is it poses big problems for cryptography. And you probably heard that being, you know, in news headlines like, oh no, it's all over. And it's pretty bad, but I don't think it's all over. It's pretty bad though. So the largest example is something called Shor's algorithm, which solves a problem. Again, don't worry about this. I'm just going to say the words, and if you don't get it, fine. It solves a problem called the discrete log problem. And this part that does matter. What that problem gives us is all the security for public key crypto. Okay, most of public key crypto. a majority of public key crypto. We'll just keep reclassifying how much I want to say here. Well, okay, so elliptic curve crypto, no, gone mostly. Well, you know, there's everyone has little niche things like, look at my quantum resistant elliptic curve algorithm, and they're like, wow, that's a lot of buzzwords. And it also does a pretty damn good job at factoring, and that wipes away RSA, so that's unfortunate. And it also, there's another algorithm called Grover's algorithm, which cuts, so it cuts the number of bits of security that you have for symmetric key stuff in half. So what used to be AES 128 is now AES 64, effectively, with security-wise. So you just need to double all your keys. Oh, but wait, AES is only defined up to 256. That's unfortunate. So again, there's things that people are coming up with to solve these issues, and I'll get to those in a second. But one thing that is like a saving grace to all of this is that your answers are probabilistic, right? So you just have a probability that those are going to be the bit value, or the observed qubit values, right? So because of that, what typically can happen is that if you have an algorithm that you want to run on a quantum computer, you take that algorithm, you run it thousands or tens of thousands or hundreds of thousands of times until you see this distribution of answers and you know which one is correct, because you'll know the probability beforehand what your answer will be correct. So that's a saving grace, right? You got to run it a ton of times before you know what the issue is, and or what the solution is. This is why it's more typically used in problems that they're easy to check, because then you don't need to, right? So if something's easy to check if it's right, you run it, you check it. You run it, you check it. You don't need to run it 10,000 times, look at the probability distribution, say, well, I'm pretty sure this is the answer, right? And then try things as you go out in your little distribution. So that's a saving grace, and that's also the reason why you're not going to have a replacement for your CPU, right? That's not going to happen because you don't want to do 2 + 2 = 4 50,000 times to figure out that it equals 4, right? You want when an ALU on your CPU, so the thing that does the math. I was about to say it. So an arithmetic logical unit. So the thing that does the math on your CPU, one of the most important things on a CPU, and almost every single instruction that gets run is going to be using the ALU, whether that's loading the instruction, figuring out where the instruction pointer, everything. You don't want that to be probabilistic, right? You don't want this to maybe go to the main function, right? You want to be sure. So that's why it's probably just going to be another onboard chip, kind of like GPUs and stuff like that. Well, that's not really on the board chip, but what?
A QPU?
A GPU?
Quantum.
Oh, yes, yes, QPU. The other thing which gets really crazy and really buzzwordy is quantum Fourier transforms. And so all those do is just make the answer you want much more likely. We'll leave it at that. So that's what they do. Yeah, so that's cool. And then we have Prime Minister of Canada. So where are we now? So in 1998, we saw that, like, I think it might have been IBM came out. They've been really at the forefront of this for a while. Came out with a 3-qubit processor, and everyone's like, "Whoa, this is cool!" Because it was first like thought of way back when in like the 70s and the 60s. And that was like physicists going like, "Huh, I bet you could maybe do something like this with computers." And the people who were like working with the computers at the time were like, "What? I have my vacuum tube and I'm fine." So, and then like it took 2 years, and we went up 4 qubits. That's not bad. And it progressed every few years or so. And as of recently, it started to take off quite a bit. In fact, I updated the slide today, and so we saw, in 2017, late 2017, there was this 50-qubit number put out by Intel. The only issue is something called coherence. Again, physics buzzword. And what that usually means is how much time you have to make your calculation before you won't be able to observe the answer, at least with not a ton of error. So basically you want that to be longer, right? You're going to do operations, they're going to take a little bit of time. So that was the only issue with that one. But as of this morning, Google put out their chip, or it's not out. They said that they're working on their chip, and it looks like it's probably going to come out sometime this year. That's 72 qubits, and that double asterisk is just that it's good shape. There's nothing really wrong with it. So that's a thing, and it's what Google's banking on, and this is what the majority of the press release was about, is that this will be the first chip that we're going to have that it's going to be able to do operations, different algorithms, doesn't matter what it is, more efficiently than any supercomputer in the world. What?
A little chip.
A little chip. A little chip. So that's cool, right? And yeah, the term is quantum supremacy. I don't know if I said that. But at least that's their definition of quantum supremacy. Everyone has a different definition. So that's cool. It's kind of scary, but it's also kind of cool. There are other things out there. So this little tidbit at the bottom, I'm going to qualify this a little bit. So I said we need about 4,000 qubits to break current RSA ECC standards. So ECC, yes, absolutely. 4,000 is enough.
What is that?
Which one?
ECC.
Oh, I didn't give that talk. So ECC is that's a big question. So it's a different form of public key crypto.
What's it stand?
Yeah, the elliptic curve crypto, and it's a different form of public key crypto that's based on elliptic curves and not prime number stuff. Kind of, because that was a terrible definition, but because elliptic curves still, never mind. So, but yeah, it just uses. Okay, that's a tough question.
Sorry. I think elliptic curve crypto, and that it's different from some other
Public keys.
key
Yeah.
algorithms. I think that's it.
Yes, it's different than RSA. And the main difference, the main thing that people like about it is that it's smaller key sizes. So you get the same benefit of 48 RSA for like 162-bit ECC. Same security. So, pretty nice. Yeah, so but this 4,000 qubit nonsense. So that will break almost any ECC out there. It will break up to 2048 RSA. So you need to go 8,000 if you want to break 4096. It scales linearly. So that's how that works. You just multiply by 2, multiply by 2. And then there's this company out there called D-Wave that's tried to make their name in this quantum world, and they're utter nonsense. So I'm just going to say that. I'm going to say that. Well, hopefully no one from D-Wave's watching, I don't think.
Maybe they're the mysterious third viewer on the stream.
So, hi D-Wave. So, they have absurdly high error rates, as well as they make their circuits in a way, they're still called circuits, that are really focused to one application. And because of that, they like squeeze in like terrible coherence times that we talked about to just fix one thing. And they're like, we can make a business plan out of this. We'll just make it like, and the thing that they get out of doing, like getting such a high noise and they have such high error rates and such low coherence time, is that they can make in press releases, they can say, we have a 2,000 qubit quantum computer. And everyone's like, whoa! And then it can't do anything. Well, it can do some stuff, but it's not much better than like a 40 qubit quantum computer, so, okay. Okay, so is this good or bad? Final recap here, or close to a final recap. For crypto, not as bad as that might have made it out to be. So we have quantum resistant public key algorithms. Oh, there's no demo, sorry. I lost that demo. So there is a sorry, where was I? Okay, so there are quantum-resistant public key algorithms out there. They've been out there since the 90s. One of them is called NTRU. There's another one called Yashi. I guess I could name them all day. I really can't. Those are the only two I know. But no one's using them yet. So that's a thing. They're less efficient computing-wise than ECC and RSA, the stuff that people use. And that's really why. And no one really wants to transition over until they have to. So that's a thing. But what you do get out of it, and this is super cool if you're into crypto and really high level here, is that these two algorithms, more Yashi in particular, are something called homomorphic, and this is just a small tidbit crypto. So what that means is that you can take encrypted data and perform operations on it without knowing what the data is. And it's totally secure. Wink, wink. Totally awesome. That's in jest. It's pretty secure. And it's super cool, right? This can lead to like encrypted databases on servers that you don't really trust, and they do all the operations and work for you, so you don't have to care. Like you're just like, all right, that's cool. So yeah, that's pretty awesome. Only thing is that these are really, really slow, like really slow. So at last time I checked, it was much worse than what I had said previously. To do for like 10 records in a database, to do a select statement, let's go, sure, yeah, is 10 minutes, I think it was. It might have been longer. It might have been an hour. I think 10 minutes is what I said last time. It's bad, right? It's really bad. So that's why no one's using them yet. But it's a race. It's the white whale of modern crypto right now, right? If you can get this fast, then everyone will love you. Well, not everyone. People, yeah, not everyone. So. Yeah, I don't think I can find this demo. So, questions, I guess. There was a lot there. Yeah. All right.
All right. Thanks, Nick. That's all that we have for the evening. We will probably not be doing another Tech Talk this semester, but keep your eye on the NextHop website and the Slack for information about whatever we do next semester. Probably not posted by me. Thanks for coming, and be sure to come to our next Build It Night in 2 weeks. Thank you.